Hi everyone, today we're going to be talking about Chapter 14, Chemical Kinetics. In this chapter, we're going to be learning about the 4 factors that affect reaction rate, calculate the average rate, do something called the method of initial rate to determine the rate law, K, and the order of the reaction. We're also going to be calculating the half-life and drawing a reaction coordinate diagram. If you're using this section study for the MCAT 2015, this is Fundamental Concept 5 and 5E. The first thing we want to think about when we think about kinetics is how fast a reaction is occurring. So anytime we can think about how fast a reaction is occurring, we're thinking about the kinetics. For example, if I have this beaker and at time equals 0, the beaker has purple molecules in it. And over time, the purple compound disappears and the green compound appears. And by the end, we'll have no purple and all green compound. We're going to talk about the factors that affect reaction rate. And one of them is the physical state of the reactants. If we have a more homogeneous mixture, the molecules will tend to come in contact with each other more quickly and will more likely make the product. A non-homogeneous mixture, for example oil and water, this reaction will require stirring or some sort of physical shaking in order to make the reaction occur. If we look at the concentration, typically as the concentration of the reactants increase, so does the likelihood that reactions will bump into each other and thus make the reaction go faster. If I use the example of steel wool, so I'm going to burn steel wool in air, which is about 29% oxygen. And if I do the same reaction in pure air, in pure O2, the steel wool ignites instantaneously. Temperature is another thing that we can change. So as the temperature goes up, the kinetic energy goes up, and the molecules are more likely to collide together with a greater energy, and we're more likely to produce product. The last example is something we have not come across in this class, but you may have seen it in your biology class. Enzymes are examples of catalysts. Catalysts speed up the rate of the reaction, but do not appear in the product and can be recycled. So biological enzymes are used to produce a certain product, but the enzyme can be recycled to do the reaction again. Anytime we have a kinetics experiment, we're always going to be collecting data. So we'll have time, and we can collect data such that we're observing the disappearance of a starting material, or we can observe the appearance of the product. So in this case, we're observing the decrease in concentration of our starting material, which is C4H9Cl, and we're going to be observing the rate of the disappearance of that compound. So if the rate is negative, it means the compound is disappearing. And if the rate is positive, it means the compound is appearing, such that you would be looking at the products. In order for us to calculate the average rate, we need to observe the change in the concentration, in this case of our C4H9Cl, over time. So we subtract the concentrations, and then we subtract the time, and it gives us an average rate of 1.9 times 10 to the negative 4 molar per second. The sign is negative because the compound is disappearing. If we plotted the data with the y-axis being C4H9Cl and the x-axis being time, we would get a curve that looks like the plot. We would see that the initial rate, instantaneous rate at time equals 0, is different than the instantaneous rate at time equals 600 seconds. So in order for us to calculate the rate, we're going to generate what we call a tangent line to the curve. So we've already done this in lab, and in Logger Pro, we use this R symbol to draw the tangent line. So if we blow up the data up in the upper left-hand corner, and we look at the instantaneous rate at time equals 0, we're going to be drawing a tangent line to create a triangle. And then we're going to be estimating the change in y over the change in x. So I estimated the change in y to be from 0.06 to 0.1, and the change in x to be 210 seconds to 0 seconds. So I get an initial rate of negative 1.9 times 10 to the negative 4 molar per second, with a negative sign out front to indicate that the compound is disappearing. So I can see that if I look at the instantaneous rate at time equals 0, it'll be a little bit faster than the instantaneous rate at time equals 600 seconds. And that is what typically happens where the reaction rate slows over time. If I relate the reaction rate to the balanced equation, I will get something like this. If I have a generic balanced equation where compounds A, B are reactants and compounds C and D are products, the coefficient of the balanced equation will be lowercase a, b, c, and d. In order for us to relate them to the rate, I will see that the change in the compound A over the change in time is multiplied times 1 over the coefficient for compound A. Same thing, 1 over the coefficient for compound B times the change in B, 1 over C, and 1 over D. But you notice that there are negative signs for the two reactants that should indicate that the compounds A and B are disappearing because they're reactants. So let's look at an example for iodic acid producing hydrogen gas and iodine gas. And so the relationship that we would have using stoichiometry would be 1 over 2, which is the 2 is the coefficient for the iodic acid, times the change in iodic acid over the change in time, and the change in iodine over the change in time, and the change in hydrogen gas over the change in time. So the only one that has a negative in front of it is the iodic acid. It's the only starting material there is. And the only one that has a fraction is iodic acid because it has a 2. These other ones have a 1 and you don't need to show them. So here's our first clicker question. So just remember as you answer the question that there's already a negative sign out front of this change in A over T. And I'm looking for the fraction that belongs in front of Okay, so I'm going to give you a second to answer the question. Okay, so you should have answered B. So when you solve the problem, you need to get the change in B over the change in time by itself. So divide by 3. So you should get the fraction 2/3 times negative 1 times the change in A over the change in time. Don't feel bad if you got it wrong. Only 25% of the class got it right. So I need to introduce you to something called the rate law. When we think of the word law, we usually think of a few sentence description of something like the law of physics. But this case, The rate law is actually an equation that looks like this. The rate equals the rate constant times some reactant, and in this case it's labeled A to the N, and another reactant, B to the M. In this case, the concentration of each of the reactants is written in green, and M and N reflect what is called the order of the reaction. So these values can be whole numbers from 0 on up. Whenever we have a kinetics experiment like this one, where the ammonium ion is reacting with the nitrite ion to produce nitrogen gas and water, we're going to have a set of experiments to go along with the balanced equation. In this case, we have 8 experiments to work with. And if you look closely at the experiments, you can see that in some of the experiments, we change the concentration of ammonium ion, but keep the nitrite ion the same. And in the other equations, we keep the ammonium ion the same and change the nitrite ion. So in order for us to visually decide what the order is for ammonium ion, for example, choose an experiment where we've doubled the concentration of ammonium ion, like experiment 1 and experiment 2. And then if you look at the rate has doubled. So very quickly we can see when we double the rate and we double the concentration, that's considered a first order reaction. So now if we want to decide what the order of the nitrite ion is, we can look at one of the experiments in 5 through 8. So I happen to choose 5 and 6, but you could choose any of the other ones. And you want to see that when you go from experiment 5 to experiment 6, you've doubled the concentration of nitrite ion, and the result is doubling the rate of the reaction. So this means that not only is ammonium ion first order, nitrite ion is first order as well. So now that we've decided that it's first order in the nitrite ion and first order in the ammonium ion, we can now write the rate law. So our rate law will be rate equals our rate constant times the ammonium ion to the first power and the nitrite ion to the first power. So K in this equation represents the rate constant. So we can do several different things knowing the rate law. First, we can calculate the value of K. We can calculate the rate of the reaction with any set of concentrations. We can determine the order of the reaction. So when we look at the exponents in the rate law, m and n, that tells us what we call the order of the reaction. So we say it's first order with respect to the ammonium ion, it's first order with respect to the nitrite ion, and it's overall second order because we add the order for the ammonium ion and the order for the nitrite ion. Units on K for overall second order reaction are per molar per second. So this is your second clicker question. So if you have the rate law, K A squared, which of the following will not increase the rate of the reaction? So pause the video, answer your question. So you should have said B. Increasing the concentration of B will not increase the rate of the reaction. This is because B is not in the rate law at all. So no matter what concentration you put for reaction B, it will not change the rate. So think about this one. If we triple the concentration of CO, what will happen to the rate if CO is second order? So pause the video, think about your answer. Okay, so you should have answered D. And in class on Friday, nobody got this question right. So when you increase by a factor of 9, you'll get a factor of 9 because you'll have the carbon monoxide is 3 times higher. And then since it's a second order reaction, 3 squared is 9. So you'll have a rate will increase 9 times. So the last discussion of the day came about with this slide. I want you to take and pause the video for a second and think about what's happening in each of these two plots. So you should be able to see that we have alcohol and it's converting to a product called acetaldehyde, and the enzyme is called alcohol dehydrogenase. So you can see that the ethanol is decreasing in concentration over time, and at about 2.5 hours, the ethanol concentration is basically 0. But the second figure shows the rate of the reaction over that 2.5 hours. So you'll notice that the enzyme has a reaction rate of 0, an order of 0. We're going to continue to talk about the ramifications of this reaction in class on Monday.